In these videos, we're going to talk about catenary rings. Apparently, some people call this catenary, but we'll go with catenary. To motivate its definition, let us look at the following wrong assumption that many of us make when first learning about dimension. When we first learn about crude dimension, it's very easy to make the mistake of assuming that if P is a prime ideal of a ring R, then the height of P plus dimension of R over P should be equal to dimension of R. Let's look at an argument for this and see what went wrong. Now, the height of P is defined to be the length of a maximal chain of prime ideals inside P. On the other hand, dimension of R over P would correspond to the longest length of a maximal chain of prime ideals starting from P. And dimension of R is defined to be the longest length of a maximal chain of prime ideals contained inside R. So we might argue that we can always combine a maximal chain of prime ideal contained inside P with a maximal chain of prime ideals starting from P to get a maximal chain of prime ideal inside R. That is indeed true, but remember that dimension of R was not defined to be just the length of any maximal chain of prime ideals. It has to be the length of the longest such chain. The issue is that not all maximal chain of prime ideals are gonna have the same length. Actually, when all maximal chain of prime ideals of R have the same length, then we say that R is a catenary ring. So let us look at example of a ring that is not catenary. We can view this ring as the coordinate ring of the union of the z-axis with the xy plane. Here the z-axis is cut out by the ideal x, y, and the xy plane is cut out by the ideal z. It's gonna have dimension 2, and the following is an example of a longest maximal chain of prime ideals. We can take the prime ideal corresponding to the xy plane, and that contains the x-axis, right? And the x-axis in turn contains some point. This is a chain of length 2, so we know that dimension of R is at least equal to 2. On the other hand, we can produce other maximal chain of length 1. For example, if P is the prime ideal corresponding to this point, then the height of P is 1, corresponding to this irreducible component containing P, whereas dimension of R over P is going to be 0 because this point does not contain any strictly smaller irreducible subvariety. So this chain is already maximal, and its length is 1, which is smaller than the dimension of R. Note that 0 is not a prime ideal because R is not an integral domain. Geometrically, it means that the whole of this variety is not irreducible. Similarly, if we let P be the ideal corresponding to the z-axis, then the height of P is 0, i.e. codimension of P is 0 because the variety corresponding to P, the z-axis, is not strictly contained inside any bigger irreducible component. On the other hand, dimension of R over P is gonna be 1 because the z-axis strictly contains a point. Algebraically, it means that the ideal P is properly contained in a maximal ideal. Thus we see that this is a maximal chain, and its length is only 1, which is smaller than the dimension of R. You see, the problem here is that the longest maximal chain in R might not always pass through a given prime ideal P. So in general, we can only say that the height of P plus dimension of R over P is going to be less than or equal to dimension of R, because we can always combine these chain of prime ideals to get a maximal chain of prime ideals, but that's not going to necessarily be the longest maximal chain of prime ideal. However, for catenary ring, since all maximal chain of prime ideals are of the same length, we do have equality. So our next question is, of course, which rings are catenary? And that will be answered in the next video.